Thanks for the introduction, Andre. Yeah, so you know, a bit about my journey in industry to begin with. So after grad school, you know, I joined Intel, and I joined. So at that time they had just gotten interested in quantum computing. So they had they had just started a quantum computing research group, and they were planning to do research on superconducting qubits and silicon quantum dot qubits. So I joined there as a quantum algorithms researcher, and my job was to, you know, design and implement algorithms that could be run on very few qubit devices. And since the end of last year, I left Intel and I've been working at IonQ, where they work with trapped ion qubits. You know, I help you know, people out in the real world to implement, you know, sort of their business problems on quantum computers. But at the same time, you know, my research interests very much lie in studying many-body condensed matter physics with these systems, and that's what I'm going to talk about today. So let me share my screen. So can everyone see?
Yes, I think so. We can see it well.
Okay, great. You know, I want to emphasize that, so I really appreciate when people ask a lot of questions. Like, I've got a lot of slides, and I'm not you know, I would be much happier if we went through only part of the slides, but everybody understood what I was talking about, and you know, I was able to answer any doubts anybody had, rather than that I get through all the slides. So please, you know, interrupt me, or if you don't want to interrupt me, I'll stop, you know, every few slides and ask if anyone has questions. So please feel free to ask at that time. So, you know, here's an overview of my talk. In the beginning, I'm just going to give an introduction to quantum computing. I'm sure many people already know, but if you don't, this will give you an idea of what, you know, the kind of, basically what quantum computer programming essentially means. And then I'll give an introduction to what are now being called NISQ computers. So NISQ stands for near-term intermediate scale quantum computers, which is basically, it's you know, it categorizes the kind of quantum computers we have today. And then I'll move to studying, you know, examples of where we studied condensed matter systems on NISQ computers. So let's begin. So the fundamental units of quantum information are qubits. So just like in classical information, the fundamental unit of information is a bit, which can be 0 or 1. In quantum information, it is a qubit. So the state of a qubit or a quantum bit is actually a vector in a 2D vector space. And an example of it is given over here. In this 2D vector space, you can pick any two orthogonal vectors and use them to define what's called a computational basis. And for instance, here you can pick 1, 0, and 0, 1, and they become the quantum analogs of the 0 and 1 state. And then any state of the qubit can then be written as a superposition of the 0 and 1 states. Can people see my mouse as well?
Yep. Yeah, we can see mouse.
Yeah. So any state of the qubit can be written as a superposition of the 0 and 1 state. So an example is given over here, right? And when you measure a qubit, the act of so even, you know, during the quantum computation, the qubits can be in superposition, but if you measure them, it will collapse. If you measure a qubit, it collapses into a computational basis state. So you can only measure it in 0 or 1. Right, and basically, if you define an arbitrary state of a qubit as alpha 0 plus beta 1, the interpretation is that the probability of measuring 0 is alpha square, and the probability of measuring 1 is modulus of beta square. And the probability, you know, since it's a probability distribution, the sum of the probabilities has to be 1, right? So it has to be normalized. Now that's about 1 qubit. What happens when we have many qubits? So as the number of qubits increases, the size of the computational basis will increase exponentially. So the computational basis is essentially the Hilbert space of the quantum system. And so for 2 qubits, you have access to four computational basis states. And for 3, you'll have 8 and so on. And to access states in this entangled basis requires entanglement. So for example, an example of an entangling operation is a C0 operation. So when you act with a C0 on 2 qubits, one in state X and one in state Y, it gives you X and X plus Y modulus 1. And then, so for instance, if you start with an arbitrary 2 qubit state and you act a C0 on it, the 0 state will still go to the 0 state, 1 will go to 1, but if the first qubit is in 1, it will flip the state of the second qubit. So 1 0 will go to 1 1 and 1 1 will go to 1 0, right? So that's the example of an entangling operation. And the reason why people get excited about quantum computing is basically if you have 50 entangled qubits, you have more states than any classical supercomputer, and with 300, apparently you have more states than atoms in the universe. So if you can process that much information in parallel, naively you might think that you have access, that might be very powerful, right? But the caveat is that the first caveat is that quantum information is extremely fragile. And so, if there's any small coupling to the environment, whether a photon or a phonon or whatever, you can basically destroy all this, the superposition of this giant superposition, and destroy all your information, right? And then another caveat comes from when you start thinking about the quantum classical interface. And the catch is that getting information, classical information in and out of the quantum computer is often not efficient, right? So typically when you start off a quantum computation, the first thing you need to do is prepare your qubits in a certain state. And typically this will be just a computational basis state or some low entangled state, right? You cannot typically start off in a very, in a state that already has a lot of information in it. You have to prepare that state. And when you measure something, you measure a system of qubits, again, it will collapse your computational basis state. And so therefore, when you design a quantum algorithm, you have to keep all these caveats in mind, right? So for example, you have different types of categories of quantum algorithms. So I've listed a few here. So one type of quantum algorithm is Grover search. So where you are trying to find a trajectory through this state space that results in a desired state with high probability, right? And this desired state could be, say, if you're trying to search a database, you want to find an element of interest, or if you're trying to invert a function, you want to find, say you're trying to invert fx is equal to y, given y, you want to find x. So you design your search algorithm to give you x with high probability. And then a second kind of algorithm is where you are trying to generate a desired probability distribution for sampling. So like I mentioned before, a wave function can just be interpreted as a probability distribution over computational basis states. And so that generating desired probability distributions has a lot of different applications, for example, in machine learning. And then, of course, there's quantum simulation where, say you want to study one physical system, you can design some mapping between the components of the system of interest to qubits, and then time evolve under the Hamiltonian that arises from the mapping, and then essentially by studying the qubits, you are studying the system of interest, right? And so, for example, things like systems of interacting electrons can be studied in this way. And then also very interesting is that, quantum computers can—
May I ask a question here?
Yes, go ahead.
My name is Pawan. So can you please go to the previous slide?
Mm-hmm.
So I see here that you have to collapse for a computational basis state. Now my question is, if I'm trying to solve an initial value problem or a problem, so let's say at every iteration, do I have to find this basis?
Well, it depends on how you design your algorithm. If your algorithm is incorporating measurement or partial measurement, then yes, it has to incorporate. Then it has to be, whenever there's measurement, you're going to measure in the computational basis. But there is a quantum algorithm that says that any quantum circuit, right? Any quantum quantum computation, the measurements can all be moved to the end. So I don't exactly know what quantum algorithm you're talking about, but in principle, you could just move that to the end and not do it after every time.
Let's just say the algorithm I'm talking about a spectral method or something that actually just marches in time, marches in time. So do I have to, like, computational basis? I believe, is it something that I can just predetermine it, or I have an arbitrary state, and that's pretty much I use the same computational basis for my whole simulation. Is it possible?
So I guess I didn't quite understand. Yes, you would probably want to use the same computational basis for the whole simulation, but it's not that hard to. So if you have any kind of what's called a product state in which the qubits are not entangled, it's typically not that hard to move from a state that's not in the computational basis to one that is in the computational basis. But that's only for that's only for simple states. So I'm not quite sure when you're saying something about starting in an arbitrary state or having an arbitrary basis.
Yeah, some orthogonal arbitrary basis function or something like that. But anyway, I guess we need to kind of revisit this question for probably later. The second question I have is how many qubits are so far achieved?
Right. So okay. So this is a very contentious question in the community. If you look at D-Wave is just announced. They have 5,000 qubits. Google will say they have, I think, 60 something. IBM has, I don't know, 50 something. But what do those numbers really mean? How many of those qubits are usable? What is the fidelity of the operations? All of those things have to be kept in mind, right? So at IonQ, I think our company is, it's a pretty scientific company. It started by two professors, who have decades of research experience. So for us, we offer, currently we offer 11 qubit systems, access to 11 qubit systems through the cloud. And those 11 qubits are actually like usable. You can entangle them all and get, some non-trivial information at the end. And just today we announced a new 32 qubit system with 99.9% 2 qubit gate fidelity, which I really think is the state of the art.
I see. Apart from the environment, what is the other limiting factor? Is there some circuitry that limits the number of qubits, or is it just the environment?
So the environment limits the operation fidelity, but there are a lot of engineering challenges that come, and that's, so the next thing I was going to talk about, right, was that quantum computers can be realized on many different platforms. So my company, we work on trapped ions. Then at Intel, and if you look at IBM and Google and Rigetti, they are working on superconducting qubits. Intel is also working on quantum dots. Microsoft is working on Majorana fermions. And then there are some more, technologies that are early on, such as nitrogen vacancies and diamond. So each different technology platform has its own challenges in achieving, in scaling up the number of qubits. So for instance, in the in the solid state technologies, they have problems of, basically interconnects, like, it's just, it's like a problem of control, right? So if you need like, five wires to control each qubit, then how many wires you have going in and out of the system? Like, how do you scale that? Like, it's a physical engineering challenge, right? And then there's problems of microwave crosstalk, things like that. In Majorana fermions, I think they have not even exhibited a single qubit yet. That there's, it's hard to sort of, it seems to be hard to conclusively determine that there, you have seen a qubit or not some other effect. In trapped ions, we know that if you want to scale up to hundreds of thousands of qubits, you can't have like a monolithic device anymore. You essentially need to have a quantum network where you have, maybe a 30 qubit system linked by a photonic interconnect to another 30 qubit system. And so then you have to think about, like, when you are implementing a quantum algorithm, how do you implement it on a quantum network, essentially, instead of like one monolithic device with all-to-all connectivity. So there are different engineering challenges, software challenges, and each different technology platform has its different challenges, yeah. And I must say that's something that you really learn about when you start working in industry, because you really want to get the whole system to work. Often, like when I was in academia, often everyone was working on like one single aspect of the system. Somebody focuses on algorithms, or somebody focuses on manufacturing a perfect qubit. But then you are trying to get something that you're trying to get a technology to work as a business. You really need everything to work end to end.
Okay, that's all my question. Thank you.
Okay, yeah, thanks for the question.
Sonika, could I ask you a quick question?
Go ahead.
So, given all of these advantages and disadvantages, another disadvantage of trapped ions, I would argue, is the anomalous heating issue, right? If you bring too many ions close to the surface, then you also get lots of heating, and that curtails scalability. But given these advantages and disadvantages, what is the niche for trapped ions? Is it really high accuracy calculations that you would use for, let's say, quantum chemistry, or is it some other niche? Because obviously, superconducting qubits are scaling a lot higher at this point.
So I would actually, I don't know if I quite agree with you. So I think, you mentioned the heating issue, but despite those kind of issues, trapped ions consistently have higher fidelity operations, right? And also they have one advantage of them is that they have higher connectivity. So in the next few slides, I'll show you examples of how the connectivity comes into play when we actually go to run quantum algorithms, right? So basically, for instance, I'll give you an example. Like if I don't know if you know these problems called max cut problems that are defined on that are defined on a graph with maybe some connectivity, and you want to, it's an optimization problem. So if you have a higher connectivity device, it's much more efficient to implement the quantum algorithm. Whereas if you have a solid state device, you have to basically use swap gates that are very expensive in terms of fidelity to optimize an arbitrary graph. And so those kind of maybe deep quantum circuits and quantum circuits that require a lot of operations between basically that are defined on highly connected graphs somehow. Those are really I think the traps will really shine on those. Is that good? Okay, if that's good, I'll move on. Can people hear me? Yeah, okay.
Yeah.
Yeah, okay. Yeah, and the interesting thing is that, for instance, quantum computing, like I mentioned that qubits are the fundamental units of quantum information. So qubit is essentially a spin half, right? But actually, to realize quantum computers, you don't really need spin halves, right? You could do quantum computation with fermions. Like nobody's, as far as I know, nobody's trying to implement this, but actually, you know, there is theoretical work that shows that you could do you could have a universal quantum computer built off fermions, right? So I think that's pretty interesting, that there are so many different physical technologies that have, you know, very little in common with each other maybe, but they can all achieve quantum computation in principle. So let's move to a little bit of the nitty gritty. So you know, when we sit down to program quantum computers, what are we actually dealing with? So here's some examples of common qubit level operations. So one thing to keep in mind is that unlike classical logic gates, quantum logic gates are unitary. So, and that basically means that they're reversible and they preserve what would be called the length of the vector, in the Hilbert space. So, for instance, you could have a Hadamard gate, which is represented by a matrix that looks like this. So a Hadamard gate basically takes you from a 0 state to a 0 + 1 state. And if you start in the 1 state, you go to the 0 - 1 state. And then you have the polymatrices, which are the, you know, X, Y, and Z, the polymatrices. So the X operation will flip the state of your qubit. So if you're in 0, you go to 1. And if you're in 1, you go to 0, and so on. And then examples of common 2-qubit operations are, for instance, the swap gate, which exchanges the state of 2 qubits. So if you're in 0, 0 or 1, 1, you stay in those states. But if you're in 0, 1 or 1, 0, you flip the order of the qubits. And then you can have, so for any one, for instance, for any 1 qubit operation, you can have control version of that. Where, you know, if the control qubit is in the state 0, nothing happens. And if the control qubit is in state 1, you act the operator U on the target qubit, like that. And so, you know, the current programming paradigm for quantum computers is quantum circuits. And it's a model in which the quantum computation is basically, it's a sequence of quantum gates. So, you know, I guess many of you might have seen a diagram like this before that represents a quantum circuit, but in case you haven't, what this shows, the way to look at this, it's just like it's like a musical score almost, right? So on the x-axis is time, right? Basically this shows, you know, so on the x-axis is time, and then on, you know, each of these lines represents a different qubit. And the boxes show the gates acting on the qubits at different moments of time, right? So, for instance, this is the quantum circuit for this is the circuit for a quantum Fourier transform, right? And you start off with the Hadamard gate. So if you Hadamard gate acting on the first qubit, and then you have these controlled Z rotations. And in the end you measure. I haven't shown the measurement, but in the end you're going to measure. Right. So does anyone have any questions about the notation?
Could you explain what the intersection between the lines means of the dots?
Oh, you mean over here?
Where you have like a dot.
Yeah. So over here, so for instance, this, right? So this is a quantum operation acting on x1 and x0, right? And the dot over here means control. So basically, what this means is if this qubit was in the state 0, nothing would happen. But if it's in 1, then the R2 acts on x0. So it's an entanglement. Right. Yeah. Thanks for that. Thanks for letting me clarify that. And then, you know, the quantum computers built by IonQ, IBM, Google, all of these people, they are universal quantum computers. And basically, you know, an easy way to understand what they are is by just saying that they can run any quantum algorithm. And the second thing is that they can usually be error corrected. And this should be contrasted with quantum simulators. So for example, many people working in condensed matter physics may be familiar with examples of, systems like cold atoms being used to implement a certain Hamiltonian. But in quantum simulators, typically you can realize only a limited range of Hamiltonians, whereas with universal quantum computers, basically you can run any possible possible quantum algorithm, which is basically a combination of some kind of unitary evolution followed by some kind of measurement. And the other interesting thing about universal quantum computers is that a small set of gates is enough to build, realize any quantum computation. So I'll give some examples of sets of gates. So arbitrary rotations around two different axes for single qubits and an entangling operation such as CX. Those three operations are enough to build a universal quantum computer. Here's another example, and then also the Hadamard gate along with the Toffoli gate. The Toffoli gate is basically a double control knot. That's universal for quantum computing. And that's quite interesting actually, because if you just have the Toffoli gate, if you just have this one, that's universal for quantum computing. That's universal for classical computing. But if you also add in a Hadamard gate, that becomes universal for quantum computing. So I think that's a cool result. Okay, so that was my introduction to quantum computers in general. Did anyone have questions? Any remaining questions on that section? Okay, if not, we'll move on to NISQ computers.
I have a question.
Go ahead, please.
Can you show us how, what is the physical configuration of the qubit? When you said you apply to a qubit, I have no clue what you mean. So show us, can you show us the real thing?
So, I don't actually have any slides prepared on what the physical qubits look like. Maybe I should have, but I'm a purist, so I was thinking about this more from like a quantum algorithms perspective. But to give you an idea, right? So, idea of what physical qubits are like, right? So for instance, for trapped ions, right, each physical qubit is just an ion, right? It's just an ion trapped in what's called an ion trap, right? And when you say you act on a qubit, it's basically controlling a laser that is used to drive transitions in the quantum state of the ion. The ion is a qubit, and then the gates are basically the laser acting on the ion, right? And
so your multiple qubit would be physically isolated ions and communicated by laser beam, right?
Exactly.
So can I imagine that you have a laser that's shooting at one particular cell with a ion in particular state, and then there's a mirror behind, and then somehow split the photon, and then go entangle with another ions. So
I think what you're describing there is more similar to a photonic interconnect. But I think what actually, so I'm not an expert in the physical implementation, but I think what actually happens is that the laser excites the ion in a certain frequency. And so when you have, so because there's single qubit operations and two qubit operations, right? And so when you have, or you can see single qubit operations and then entangling operations, and they have different modes of implementation.
So right? Where do the two trapped ions, how far apart are they?
They're probably very close to each other, but I'm so sorry. I don't have, I'm not the experimentalist here, so I can't give you the exact number, but I do have that reference over there if you want to go and check it.
Okay. All right, thank you.
Right, if you just want to like take a snapshot of that reference, that will tell you the details of the experiment. But in general, to give you an idea of the scale, right, like the 11 qubit experiment, the trap would maybe be, you know, it wouldn't be, you know, I don't want to say things are not correct, but it wouldn't be very large, let's say.
Okay.
And you know, and you know, like maybe with quantum dots, you know, that's another example. For you know, quantum dots are basically, you know, just two. So each qubit is just, for instance, an electron trapped in a quantum well, right? And so, for instance, over here there are two electrons trapped in two quantum wells, and when you want the electrons to want the qubits to interact, you lower the barrier between the quantum wells, and when you want to isolate them, you raise the barrier between the quantum wells, right? So that's kind of the physical realization. And then, right, so on and so forth. But yeah, I'm sorry, I'm not the best person to ask for details about the experiment.
That's okay, that's good.
And you know, I think that's actually a testament to the field that this level of abstraction is possible now, that I can think about quantum algorithms and implement, go in and implement them and look at the results, and I don't really have to worry about what's going on at the level of the lasers or the ions, right?
Okay.
That's actually, that's not, that's basically happened in the last, I think, 4 years, right? Basically, when IBM put its machines on the cloud, that's when people really started, there was a shift in the level of abstraction in the field. Right. So let's move on to the definition of a NISQ computer. So basically that means near-term intermediate scale quantum computers. It's a popular term, but what do people actually mean by that? So basically with NISQ computers, we mean that there is some restriction on the amount of quantum resources. So typically, you know, you would not have very many qubits. Typically, the number of qubits would be less than 100. And these qubits are not error corrected, so computation time is going to be limited, right? And so with these restrictions, when we design algorithms for NISQ computers, you try to incorporate error resilience, or basically resilience to the noise in different ways. And so, you know, some techniques are, for instance, designing hybrid algorithms that, you know, do part of the computation on a quantum computer and part of it on a classical computer. You know, there's several papers published on this now, but unfortunately, we don't have very many proofs on how this kind of computation will work. And so it's mostly heuristic, like people running numerical experiments or people running experiments on actual machines. And then a variety of a quantum classical hybrid algorithm is, for example, what's known as the quantum approximate optimization algorithm. So it's basically you construct an ansatz for a circuit that has a short circuit depth, and you try to use that to minimize some target cost function. But the advantage of it is that you work with short circuit depth, so you're less susceptible to noise. And then another way of trying to remove the effect of the noise from the answer is to incorporate symmetry-based post-processing, and this has actually been really, I found this to be really useful in my work. And then another interesting technique that we found recently, not recently, but that's really been shown recently is, you know, that's been shown recently is by incorporating partial measurement into the circuit. And that's basically, you know, it's a variant of quantum error correction. So basically, if you think about quantum error correction, the idea there is to, you know, is to form logical qubits. So at the level of each qubit, you try to remove the effects of the noise. But instead, you can apply some of the same ideas about projecting out noise at the level of the algorithm itself. So if you have, for instance, an oracle, I don't know if people know, but you know, if you have a quantum circuit where you know if you have a part of a quantum circuit where you know that at the beginning of the quantum circuit and at the end of that portion of the quantum circuit, some of the some of the qubits are going to be in a computational basis state that you know beforehand. You can measure those qubits, and if those qubits mid-circuit, in that mid-circuit measurement turn out to be in the wrong state, then you can stop the computation and start again. So if you go to this reference, there's a very nice example of that. And then also, again, you can construct problem-specific noise models followed by custom error mitigation techniques. So if you know the quantum computing platform you're working on really well, you probably know what the noise model. You probably can define. You can probably develop an effective noise model that characterizes the operations on a platform, and then you can design a custom error mitigation technique for that specific noise model. And this is also, I've found a lot of success with that. So, really, when you have these NISQ computers, you really have to sort of co-design the quantum algorithm with the machine in mind, and then you can get very cool results. So any questions on this? No, okay. And there's a lot of doubt about whether these NISQ computers are going to be useful for anything or not. That, after all, they're noisy, they're error prone. But I don't know if this is common knowledge, but basically classical supercomputers are very error prone as well. If you think of the next generation of classical supercomputers, which are basically exascale machines, there is no guarantee that they are going to work at all, right? And it's just a problem of scale. So if you have that many transistors, one or the other is going to fail during your computation, and that could be due to a component failure, a voltage surge, some radioactive material that's used in the computer, a cosmic ray, whatever, right? So the next generation of classical computers is going to be noisy as well, right? And so if you go, this is a really interesting article called "Supercomputing's Monster in the Closet." And so if you go in and read this article, you find out that many of the techniques that they propose for running algorithms on this next generation of classical supercomputers is just the same as the same mindset as designing algorithms for NISQ computers, basically trying to make those algorithms for exascale computers resistant to noise, incorporating some resilience to bit flips and things like that, right? So in some sense, for the next generation of computing, whether it's classical or quantum, algorithm design has to take some tolerance to errors into mind, right? Any questions on this? If not, let's move on. Currently, on a current quantum computer, the architecture is fairly simple compared to what a classical computer looks like. Basically, somebody like me would design a quantum algorithm and then program it in one of the quantum software platforms, which will have a quantum compiler, which will turn it into low-level code. And then this can be submitted to a qubit simulator if you want to check the correctness of your algorithm for small number of qubits, and otherwise it will go to a quantum processor. Right. So now.
Sorry, can I ask you quickly? What does it mean to have a quantum assembly code? Is it like a set of operations to the laser to turn and point and shoot, or yes, what does it look like?
It could be just as simple as this list of gates, right? So H acting on qubit 0, control RZ acting on 1 and 0. So just the list of gates, right? So that's a slightly higher level, but obviously, the low-level laser does not know what H means, right? So then there would be a slightly lower level language that would be talking to the FPGA and telling it exactly what signals to send out. So that's all it means, a list of instructions. It's very similar actually to what would be used what you would mean by that on a classical computer.
I just want to make sure it's classical information.
Yes, yes, it is. So the only thing quantum in this stack is this, the quantum processor. Everything else is, the word quantum means that it's for the quantum processor. But this is the only thing that's physically, doing quantum mechanics, obeying quantum mechanics. Everything else is some classical representation of a quantum operation, essentially. And so, so I'll give an overview of, overview of how to think about NISQ architecture. So, how to think about NISQ architecture from the point of view of connectivity graphs. So we were discussing earlier the differences between different quantum hardware platforms. So ion traps have an all-to-all connectivity graph, which basically means you can entangle any qubit with any other qubit, right? So you can, in one gate, in one step, you can entangle anything with anything else. However, with the solid state platforms like, superconducting qubits or quantum dots, you will typically have a 2D connectivity graph, which could be like a ladder like this, or a square lattice like this, or some other designs as well. But this will be typically what's possible with the solid state platforms. And then, some of the initial solid state platforms, they just had, for instance, linear connectivity graphs. And you can see why this would be appealing, because you need basically a lot of wires to control, solid state qubits. So those wires can come in from the side. Over here also they can come in from the side, but over here it's more complicated, because if you want to control a qubit in the center, how are you going to, bring your wires in? Either you come in from the top, or you have some kind of multiplexing scheme or something like that, right? So, how do these different connectivity graphs play into the implementation of the algorithm? So for instance, let's go back to the quantum Fourier transform. So we discussed this before, right? So you can see that there are 2 qubit operations between all possible pairs of qubits. So 1 and 2, 1 and 3, 1 and 4, and so on, then 2 and 3, 2 and 4, and so on, right? So 2 qubit operations between all possible pairs of qubits, right? And so you would think that this is most naturally suited to an all-to-all connectivity graph. But say your quantum device has just a 1D connectivity graph, how can you efficiently achieve a QFT on that, right? And basically you have, and we found, and this was when I was at Intel, we found that you could use swap gates basically in a smart way, so that you could have very low overhead in the implementation of the QFT on a linear connectivity graph, right? And then, going further, if you wanted to implement it on a ladder, like a 2x(n) connectivity graph, how would you do that? And basically, there we discovered that the best way was to execute 2 copies of the QFT on the lines in parallel, and you intersperse those, 2 parallel QFTs with, controlled phase gates between the legs of the ladder. And again, you could find a schedule that was close to an all-to-all connectivity. And, and so on and so forth. So, for instance, if you have, a Toffoli gate or a multi-control gate, how do you achieve that? And there we found, the best way was to use ancilla qubits and map the connectivity graph of the algorithm onto a binary tree like this, and then achieve that on a 1D. For instance, if you had a 1D connectivity graph, you insert swap gates to achieve the desired operation. And you can do that on a ladder. And so we considered all these different cases. And so this is just an example of nowadays, if you want to do quantum programming, what that looks like, right? Like how do you have this? So for a long time in quantum computing, there were experimentalists that were working on qubits, and there were theorists that were working on quantum algorithms and trying to prove, complexity theoretic bounds. But now, now that quantum computers are here, we actually have this very interesting area of how do you take this theoretical algorithm and implement it on the device, right? and you get to a lot of interesting problems that way. So are there any questions?
Could I ask about encoding classical information to the computer? So is the idea that you have like 32 qubits, each qubit can be assigned a classical bit and then it propagates throughout the system, or what?
Yes, it's the what do you mean by it can be assigned to a classical bit?
Well, I just mean, how do you encode the classical information to the system? I mean, for example, if you talked, I think, about having now a 30 qubit system, I think is what you said, right? Does that mean that you can only encode so many classical bits at a time, or what is
well,
that?
in principle, you could have 2 to the 30. So if you have 32 qubits, right? So if you think of writing that down as a wave function, you have 2 to the 32 amplitudes that you could encode, right?
Oh, I see. So you are actually able to encode the information.
So in principle, that 32 qubit system can store 2 to the 32 amplitudes at the same time, right? In principle. But how do you, but then actually doing that is a different story, right? There are experimental problems in terms of it's very fragile, and then also there are theoretical problems about if you have 2 to the 32 numbers, right? Getting that information into the quantum computer has to at least scale as the size of the data structure that you're trying to put in, right? So, so typically, that doesn't work, right? You don't want to design your quantum algorithm to store. It starts off with storing a large amount of classical information. Those are probably not the applications that will work the best.
So can I ask, in the case of the Fourier transform, how do you encode I guess you have some kind of a signal. Is that what is meant to be understood by the X inputs that you had? That's this kind of the signal that you're putting in, or?
So in the Fourier transform, say you have, so it doesn't actually have to, you can act this circuit on any quantum state, right? So you have your incoming quantum state over here, right? And then these are the gates that you enact on the qubit, right? So for instance, the H gate will be a combination of single qubit rotations. So those will be achieved by some kind of laser pulses, right? So this will just be a combination of laser pulses and then so on and so forth, right?
This machine, this quantum Fourier transform, does it actually? I assume it computes some kind of Fourier transform of some signal. So basically, I'm asking, how do you encode that signal into the machine?
Oh, and that can be different things, right? So it has a lot of different applications. So for instance, the quantum Fourier transform is used in, for instance, the Shor's factoring algorithm, right? And so there is a whole state preparation step. If you go in and look in the book Nielsen and Schwang, so there will be another circuit that can be designed for the problem that you have in mind, right? So for instance, it's also QFT is also used in what's called the quantum phase estimation problem. So if you want to find the eigenvalue of a matrix, right? And so in that there's a whole separate circuit that encodes the signal, as you're saying, in the qubit, in the qubits. And then this one efficiently finds the frequencies.
I see. So you're not necessarily feeding in classical information as a signal, something like that.
No, you would no.
I see.
Everything is quantum. You start off the qubits and let's say the grounds, like everything being 0, and then everything that acts on it is a quantum operation.
Okay, thank you.
So there's only 10 minutes left, but maybe you can look at one example of studying a condensed matter system on NISQ computers. Basically, many-body condensed matter physics, we study phases that arise from the collective behavior of many interacting particles. So things like many-body localization or the quantum Hall effect or high-temperature superconductivity. And the special thing about these phases are that basically they exhibit emergent phenomena that are very different from the underlying elementary laws. They're typically, you cannot study them efficiently on classical computers. Because the size of the computation will scale exponentially with the number of particles in the system. So instead, we hope that we can design quantum algorithms to study these phases on quantum computers. And these quantum algorithms, the conditions are that we want the quantum algorithm to scale polynomially in the size of the system, and you want it to be resilient to noise, right? Because quantum computers are inherently noisy. So in this talk, I was planning to study, discuss a few different systems, but instead I'll just maybe talk about, maybe I'll talk about the second one. But, in my research, I've worked on several different, studying several different kinds of properties of condensed matter systems on quantum computers, whether they're thermal properties, whether they're dynamics, whether it's, measuring something like the entanglement entropy. And, all the experiments I would have described would have been conducted, would have been on 3 to 7 qubits on a ion trap system where the connectivity was all to all. And the very special thing was, all of the experiments in this talk that I prepared were simulating a different many-body system, completely different. So whether it was a many-body localized system, whether it was a thermofield double state, whether it was a Fermi-Hubbard model, but they were all implemented on the same universal quantum computer. So this really shows shows how versatile these universal QCs are. So Anna, is there time or?
Oh, we have 6-7 minutes, maybe 8.
Okay, should we just stop here then and like have more questions? But
can you say a few words about one of the applications?
Yeah. So I'll describe, for instance, an easy experiment. Not this one, because this one was more complicated, but so this is one of the easier experiments to understand, I think. So many of you may be familiar with the phenomena of many-body localization. So basically, if you have an isolated interacting quantum system, if you add some disordered potential to the Hamiltonian of that system, if the disorder is large enough, there can be a phase transition from a thermalized to a localized phase. And the special thing about localized systems is that they never reach thermodynamic equilibrium, and they have all these properties like memory retention, logarithmic entanglement growth in time, etc. And there's so many open questions, since classical simulations, especially near the phase transition, will scale exponentially with system size. They're also challenging to study on quantum computers because the localized phase is extremely sensitive to coupling to a heat map. So we designed an algorithm to study MBL on a noisy quantum computer. And we did that by probing what's called the spectral function of local operators. And the spectral, so if you're given an operator A, the spectral function will just be defined in this simple way. And it has this function has some interesting properties in the localized phase that are very different than in the thermalized phase. For instance, near zero frequency, it has a soft gap versus the thermalized phase, which does not show that gap. So, basically we found a way to measure that spectral function on the quantum computer by performing time evolution under the Hamiltonian. Very quickly for that, the model that we studied was the Heisenberg model with disorder, right? And the first thing you do when you want to do time evolution typically is you trotterize the Hamiltonian. So basically, you enable that Hamiltonian to be realized by 1 and 2 qubit gates. And when you want to do that, you'll have to discretize the Hamiltonian, and that involves some error. So you do a lot of error analysis on, you know, is your discretization technique robust to that error or not? But basically, for time evolution under that Hamiltonian, we designed a quantum circuit, and we studied this one on a 3-qubit system at 3 different values of the coupling, of the Heisenberg coupling. We studied it for various realizations of the disorder. And so I'll describe the results quickly. So we measured, so the top panel, for instance, shows that, you know, our measured spectral function as a function of frequency. And you see that the solid lines over here are the theoretical value, and the blue points are the experimental value. And this is for different values of J. And you see that while the experimental value follows the trend of the theoretical value, it's almost, if you didn't have the theoretical value in front of you, all 3 curves would look pretty much the same, right? And then we found that we basically designed this technique that if we divide, if you're not looking at just the spectral function, but we look at the spectral function divided by its value at 0 frequency, you can essentially remove all of the noise, right? So the normalized spectral function is robust to any amount of noise in the quantum computer, right? And we were able to get very good matching with the theoretical values. So this was an example of, you know, we had a physical problem, a physical system that condensed matter system that we wanted to study. We designed an algorithm, we implemented it on the quantum computer, we looked at the results, they were not very good. And then, so we designed error mitigation technique that basically improved the results and showed that we can extend these circuits to bigger system sizes without significant fidelity loss. So that's a very quick overview of what's involved in studying a condensed matter system on a quantum computer. And then I'll, you know, skip over this, and I'm happy to send people my slides if you want to just go over it and get more references and things like that. And I just, you know, this whole talk, I was focusing a lot on NISQ computers and what can you do with small numbers of qubits, etc. But as a testament to how fast moving this field is, last week, one of our co-founders, they actually demonstrated logical qubits, right? So it may be possible that all this discussion about NISQ computers, it's not going to be there for many years. We're going to move into the fault-tolerant regime very soon. And also today, our company had an announcement about the 32-qubit system that I told you about with 99.9% fidelity. So the field is super fast moving, and you know, many of the results and techniques that we're designing today may be obsolete tomorrow. But if there are any students that want to get into it, I think it's a really exciting area to work in.
Thank you.
Yeah, that's the end of my talk. If there are any remaining questions, I'm happy to answer. Mostly, I think it was okay, right? That we went over the introduction more slowly.
Yeah.
Versus the detailed implementation.
So questions? Raise your hands or just speak.
I guess I have a question. Actually, I was just wondering, because I guess you got cut off for a little bit of time. So you showed for your MBL example that basically you were able to run a quantum simulation and match the data. But I was wondering if you could just say a little bit about what you learned from doing that quantum simulation, as opposed to, or what you learned from actually solving this problem on a quantum computer from just, as opposed to just doing the experiment.
Well, so there are 2 things, right? So of course it's 3 qubits, right? It's trivial. You can probably do it on your cell phone or something like that, right? But you learned how to implement it on the quantum computer, how to, you know, a priori, I don't think it's very difficult to guess that this technique would have worked, right? You need to run it and then look at the results, and then, you know, we analyzed the noise model and saw that it matched the experimental results, etc. Right? So, so you learn how to run it, basically how to implement a theoretical algorithm on a noisy quantum computer. And then what happens is when these quantum computers scale up, right, it's at 32 qubits, when it gets to 50 qubits, then you can start studying models that you cannot study on a classical computer and that you may not easily be able to find an experimental system for, right? So it may not be, so for every model of interest, for instance, there may not be a corresponding experimental system that's easily accessible, especially if you're a theorist, right? If you want to do computations, you know, on these correlated systems, it's not that easy to find an experimentalist and ask them to design their cold atom simulator to realize your Hamiltonian of interest. This is I think.
I mean, some might argue that the point of physics is to learn about experiments. But I guess I can turn my question around and just say, is there insight that you gain into the condensed matter system from doing the quantum computing simulation versus trying to simulate it elsewhere? And then I'll just kind of add to this because I saw you flashed over it and I'm interested in it. You could even comment, in particular, you flashed over a quantum phase transition. Is there insight that you learn about quantum phase transition from?
Yeah, and the idea is that you would, right? Not if you have 3 qubits or 10 qubits, but if you had 50 qubits, right? That's a computer. I'm not treating this as like a science experiment anymore. It's a computer. So for all the arguments about, simulating physical systems on classical computers holds there as well, right? So for instance, an example is, high temperature superconductivity. It's still not understood what the mechanism for that is. And one of the reasons, I mean, there's a lot of theoretical work, but also one of the reasons we don't really understand it is because we can't simulate it, right? The phase diagrams are not clear, but if you could simulate it on a universal quantum computer, you could see what the phase diagram looks like for the Fermi-Hubbard model in different regimes pretty accurately. And that would help you, that also, in my experience, the numerics often guides the theoretical work that then, you can use to understand nature properly.
I see. Okay, thanks. I think Brad has a question.
Yeah. Just feel free to speak up.
Yeah, thank you for that talk. That was really nice. I have a question about something that you discussed in the first part when you were talking about different applications. And as an example, you mentioned generate a desired probability distribution for sampling. So my question is, if you use a quantum computer to generate a distribution and you're sampling from it, doesn't the wave function collapse each time you sample from it? And so you end up having to generate that distribution multiple times?
Yes. Yes, that's true. And the idea is that, yes, so if you want, when you have the probability distribution, say you want to, calculate the expectation value of some random variable, right? So you would have to repeat the experiment many times to get an expectation value.
Right, so then it's not so clear that a quantum computer is giving you a big advantage if it's slow compared to a classical computer.
No, that's not true, because typically, the number of times you repeat the experiment may be fixed, or it may scale polynomially with the size of the system. But in the cases where you would have an advantage, generating that probability distribution even once would scale exponentially with the size of the system. So that would give you the advantage.
I see. Okay, thank you.
Yeah. Go ahead.
Sonika, I had a quick question because this comes up in a lot of computing cases. So you were talking about mapping algorithms to networks. You're a little bit constrained in exactly which networks you can use, but are there automated ways of doing that? Do you use machine learning techniques to allow you to actually map to the optimal network?
So currently, mostly there are not machine learning. I mean, there are what are called compilers, right? And schedulers and mappers that are automated, and people are exploring a lot of different ways. I don't know if there are any compilers I've seen that use machine learning techniques per se, but that's a good idea, right? It's still very much like, I'll say this, like quantum software is very much in its infancy, right? So there's a lot of room for improvement. In fact, there was some recent paper that constructed a set of benchmark circuits, and then then used all the publicly available quantum compilers, like whether from Google, some startups, IBM, etc. And they found that they were all really bad. Right? That if you did an exhaustive search of the best mapping, it was like 5 or 6 times better. So, and that's not the case in classical computing, right? In classical computing, there's decades of research in having the best possible implementation of higher level operations.
Thank you. Very nice talk.
Are there any more questions? Okay, so maybe it's a good time to finish. Thanks a lot, Sonika, for coming and letting us know about your work. It was very nice. Yeah, and if you guys have more questions, just feel free to reach out. And if you're ever interested in using that, here's a like advertisement for my company. If you are interested in accessing the IonQ quantum computers, you can do it through Amazon Web Services, or you can, if you have like a bigger research project in your group, you can reach out to me or reach out to us on our webpage, and we can set you up with access to our system through an API. Awesome. Thank you. Okay, bye. Thanks a lot.